Hello, everyone. We're going to get started in a few moments here. Alrighty, we're going to get started in a moment. Okay, alrighty, let's get started. So, my name is Mohammed. I'll be your year 11 tutor for today. A lot of you probably already know me, um, but for those that don't, um, I am a Canadian, moved over here to the UK for medical school. Um, I've been teaching for about 10 years. I started off teaching English mainly, and then I moved into the sciences. I've worked on curriculums for elementary schools and high schools. I ended up working for a high school, mainly online. It went pretty well, and then I started medical school, so I couldn't continue with that. So I've been tutoring. I'm a personal trainer at a local gym and a medical student. So very busy, but it's been exciting. So I deal with a lot of people. I love education. I love teaching people, something that I enjoy a lot. I have a bachelor's degree in human kinetics, so a lot of anatomy, physiology, and then I did my master's degree in medical physics, and now medical school. So it's been quite an adventure. Um, but yeah, in terms of things I like to do, I like athletics, working out, things like that. I also like to read, watch TV, spend time with family and friends. Yeah, typical things. Um, so I'm a third year medical student, so that means I'm mostly out and about within within the hospital setting and surgery setting. Um, so I see a lot of patients, and what I like to do with these classes is I like to add in what I see in clinical practice to what we see, so it kind of sticks. Because a lot of you guys are thinking about pursuing medicine or becoming doctors, and it's always nice to attach things that we kind of see and hear about in school with how they present with patients. So it's very, very, very interesting. Um, Yeah. In terms of the content for today, we're just finishing up this month's topic. Typically, what we do, we start off with a booklet just to ease into the session. It'll be a kind of review from the last week, and then we'll go over content. We'll do some practice questions, and before the practice questions, around seven, let's say 7:15, uh, until 7:20, we'll have a break. So 7:15 to 7:20 we'll do a break, and then we'll do some practice questions, and then we'll have a book it at the very end just to tie everything in. And that'll be it for the month of January. So that's exciting. So we have a question here. Did you pass the exams the first time around, or did you take another degree then get into medicine? I'm not sure what you mean. Um uh I when I did my exams, I did them closer to when I was done my masters. So y- I don't think it's like a pass fail. I think it's just you just have to meet the cutoffs for the universities you apply for. So there's not a specific grade associated with it. It's more so you make yourself competitive when you apply. Hello, everyone from everywhere around the world. We're gonna get started. If you don't get enough marks, you typically get another degree to get them into medicine. Yeah, that's true. So, for example, if you aren't competitive enough in your undergraduate or A levels, you might not be able to get in. So, you decide to do a degree, an undergraduate degree, and then try to get in that way. So, yeah, that is true. Okay, let's get started with the blockade. Where was it? This one. Okay, we'll do battle royale. Okay, someone said crypto, so we'll do crypto. We'll do it for 8 minutes. There we go. All I want you guys to do is just and the thing is it's either this or Kahoot. You know what I mean? I'm just trying to make writing and answering questions as fun as possible. So Blooket does a pretty good job in doing that. Kahoot kind of gets a little bit boring. That's why I kind of change things up from time to time. I wasn't from the commerce. I'm not sure if I said that, but I never said that. I was always sciences. I've always stuck with sciences. That's my thing. But yeah, there's nothing wrong with absolutely. There's nothing wrong with going from commerce to science. It happens. Sometimes you're in the field, you're not really enjoying it, so you kind of make a decision to swap over. And the beauty of the UK is you have the ability to kind of move about relatively easily. So there's about 56 of you in the session, so let's try to get a little bit more. We're gonna start in a minute. We're gonna get started. There we go. Be careful with the names. If I see something that is inappropriate, I'm going to be removing them, okay? We got about 3 minutes left. About a minute left. The university's favorite applicants with four A levels or his having an APQ. All right. It depends on the. It depends on. I think it depends on the how competitive the programs are. It really comes down to that. But I'm not in terms of A levels, I'm not too familiar with them. The moderator will probably have to answer that. Alrighty, we're getting close. Is it gonna be N that takes it? I believe so. Rory, third place. Second place, Kit. And nice, good. Alrighty, let's get with our session material. Okay. So last class we went over concave and convex. So just a quick recap. Convex, you're thinking outwards. You're thinking that the light is going to hit, it's going to hit across the plane, right? And then because of the surroundings, because of how the lens is created, it's going to go inwards, very similar to how the eyes work. So what they're doing is they're trying to bend light so that it hits the back of the eye at a specific focal point right here. Okay? So that's convex. Now concave, it's kind of going in as if you're going into a cave. That's how I remember it. Concave. It's going in. So what is it going to do? It's going to take that light and spread it outwards. Okay? It's going to spread that light outwards. So that's kind of the difference between the two. So if we were to kind of look at these two and kind of compare, so light passes through, the light lens bends the light towards each other. So convex converging the rays into a single point. Concave, it's diverging. So pushing away, bringing the lights away. Now convex, they're kind of thicker at the center. So if we were to draw it, convex like this, it's thicker in the center and thinner at the edges. Okay? And then with concave, it's thicker on the edges and thicker at the edges and thinner at the center. Now, converging lens because of the converging rays. Diverging lens because of the diverging rays. Now we use convex, and that's for correction of long-sighted. So convex is for long-sighted problems with vision. Concave is short-sighted. So the convex is called positive lens. Concave, negative lens. So like we said, human eyes, cameras, they use convex. Now lights, if you think about it, when you flash a light, let's say you have a flashlight, right? It's flashing light outwards. Why? Because it's using a concave. It's bending the light so it flies outwards. It's not going to be zoomed in. It's not going to be going to a singular point. So that's the one big one. Lights in general, like when I look at the light behind me, that's a concave lens around. So it's allowing the light to diverge outwards. Okay. Now we're going to talk a little bit about a real and virtual image. A real image is formed where the rays of light are focused. So this is a focusing of light that gives us what? The real image. Now, this real image, it can be projected onto a screen. Now, what does this mean? When we look at it, so this is the object. The rays are being broadcasted out. Yeah, so biology has it too. Guys, I don't know what you're talking about in terms of football and stuff. Just don't worry about it. Okay? So there is magnification in biology as well, but let's focus on the physics right now. So as we can see here, we have an image that's going to be projected, and it's going to be projected in a very similar way. Now, what's interesting is our eyes actually, this tends to happen with our eyes. So we see the objects flipped over, and then our brain kind of readjusts it. That's typically what happens. Now, when we're talking virtual, we're talking an image that comes from behind the lens. So it's an image where the rays of light appear to come, but they don't in reality. Okay, so if we look at this is the image, this is the object, and this is the image that's happening. This is a virtual image, it's not a real image. And what is happening is it's happening behind. Okay, that's kind of the idea here. So let's relate both concave and convex to whether they present real images or virtual images. So when we're thinking about convex, and how does that look like again? So convex, these are the lenses. So it's very thick in the center and thin on the outer parts. They are able to produce real and virtual images. So whether an image is real or virtual, and that all depends on where it's positioned in comparison to that lens. Now it's very simple. So convex, it can be either or, it can be both, okay? It can be one or the other. At concave, they only present virtual images. All right? With concave, they only present virtual images. The reason being concave can only present virtual images, if we take a look at the lens, and we have a lens like this, we have a concave lens. Now, it only happens with virtual because concave lens cannot be received on a screen because the incoming rays are divergent. With convex, they're convergent, they're coming together. But with concave, they're divergent. So you have light hitting here and here and here, right? But this light source is gonna be like this. And this one might go the straight, but this one's gonna turn upwards. So you have light that's being scattered. That's another way of thinking about it. Concave produces scattering light. Okay? So it's scattering. Like the light behind me, like the flashlight. So for example, if I were to turn the flashlight off in my turn the flashlight on in my, see, you can see the light scattering outwards. That is what we're thinking about when we're thinking concave. Why? Because when you put a light, that lens is going to shift that light outwards, whereas with convex, it's going to shift the light inwards. So it's converging. Okay? So in terms of real image, let's go through it one more time because some of you are asking for explanations. Okay? So a real image, where can we see this? In convex. Convex is an image that is formed where the rays of light are focused. Focused how? Focused how? They're focused in one specific area. They can shine in one specific area. So a real image is an image that can be projected on a screen. That's also true. So the rays of light are focused. That is what a real image is. Now, a virtual image appeared to come from behind the lens. I understand. Do you know how I can remember it though? That's what I'm saying. With a lot of these, it's repetition. It's repetition, seeing it and practicing it. Practice questions. That's what we're going to do. Now, if we're talking magnification, we spoke a little bit about this last month, but we're going to speak about it again. And this is the idea of magnification. I don't understand your question. Screen where? Behind the lens? What do you mean by screen? When did I say screen? Oh, you see, oh, you mean here? That can be projected onto a screen, like a screen in front of you. Like a projector, that's how it works. It's taking the information and projecting it onto a screen. That's what it means. Like how a projector works. Yeah. Virtual images are the images that happen behind the lens itself. So if you take a look here, the ones from behind, it's not going to be projected forward. That's what's not going to be a like images in a mirror. Exactly. Very good. Those are virtual images. Exactly. Okay. So magnification. When we're thinking magnification, what we're trying to do is change the size of an image by using lenses. So we're changing the size from its actual size. So magnification of lens, and this can be calculated through a number of ways. So magnification is the image height over the object height. So that's how you want to measure it. So if it's 1 to 1, magnification is going to be 1. It's nothing. Sorry, 1 to 1, yeah, it's going to be 1. It's nothing. Now, if the image height is 2, object height is 2, then that's the same thing. It's 1. There's no magnification of just 1. So magnification is just a ratio of two lengths. That's why it doesn't have any units. So when you're thinking magnification of 2, there's no units for it because it's just a ratio. So magnification is 0.5, for example. What does that mean? I said 1. When I said 1, I said a magnification image height of 1, object height of 1 is 1. 1 to 1 size means that the image height, the image that you've magnified, and the object height is the same. So that means that there's a magnification of 1. That's it. It's not 2 times, it's not 3 times. Because, for example, if the image height was 3 and the object height, the actual real object, is 1, that means that there's a magnification of 3. So you're getting almost 3 times bigger size in the magnification. So, for example, if you were to take your phone and hide it behind like a lens that that magnifies the screen, and you are measuring it, and it's about double the size, so magnification is about 2 times. That's what it means. So 1 to 1 ratio is the exact same. So if I'm looking at my screen and I put a sheet of glass in front of it, and that's the same size in terms of the image, it's a magnification of 1. Man, you guys really need to improve your writing. It's very hard to understand what you guys are saying sometimes. So my phone camera actually what I look like or distorted? So with phones, it's a little bit different. The reason being is that there's software that improves the image quality, so it kind of plays around with like the saturations or the contrast with all these types of things. So it might add a little bit of beautification or some light editing when you take a picture. It's going to be very similar, but it's not true. Like it's not 100%. I have a broken hand, so my bad. Okay, I'm not saying like you can spend like an extra second just typing in complete sentences. It's all good. I'm just saying what I've noticed is a lot of you, but when I take a picture, I'm still ugly. I don't know how to respond to that. No one's ugly based on what their moms say. Anyways, so we're gonna try this example. Calculate the magnification of an object that is 10 centimeters tall and forms an image of 250. So how do we do this? Magnification, we know it's the image height. So the image is the like the what was projected. So the magnification. This is the end product after the magnification. Okay? That's how I remember it. Object is the true object in front of you. So the object is 10 centimeters. Okay? And then we have an image that it created based on this magnification. That's 250. So we take 250 divided by 10. That gives us a magnification of 25 times. So what does that mean? That object was magnified 25 times its original height. Does that make sense? So the object is 10 centimeters tall. Okay? The image that it formed, when we think of the image, is 250. Right? So we got an image that is 25 times taller than the original, than the object height. Now we're going to try this one. Calculate the magnification of an object which is 1.2 meters tall and forms an image of 1 centimeter. So the opposite now. But the first thing we got to do is there's two different units. So we got meters and we got centimeters. You could convert the 1.2 to centimeters, or you can do the other way around. But here for this case, we'll do it 1.2 centimeters to meters. So it's 1.2 meters to centimeters. So 1.2 centimeters, 1.2 meters equals 120 centimeters. So we take that same formula. So the image height, the image is 1 centimeter tall. And the object height is what? 120. So that gives us a 0.008 magnification. So that means that the image has been lowered by a lot. I get that, but you don't when you guys are writing, just pay attention to how many decimal points, but it's completely fine to sum it up like that. Because what value does the extra 3 give you? None. Okay, so let's review. Quick summary. So what do we know? Lenses are pieces of glass, and they can either concentrate or disperse light. So they can converge into a single space, or they can disperse. Converge, like what our eyes do, diverge, disperse, like what lights do behind me. Okay? Lenses then use refraction to converge, diverge light beams, and these lenses can either be convex or concave. We know that. and lenses can produce real virtual images. Magnification, this is an important one. So magnification is height, image object height, and it has no units because it's a ratio. That's a very important point. Now we talked about this. I'm just going to move forward here. So going back to the light spectrum, will we have to convert it to standard form in the exams? You might. When it is very high or small, or if the question says exactly. But I would say most of the time you guys won't even need to do that. But honestly speaking, if you get in the habit of just writing it the way you guys are, so exactly what you see on the calculator, you can't be docked marks unless it specifically says use only 3 decimal places, right? If it says use 3 decimal places and you put 5 or 6, I don't know if it's a good idea. So just read the question very carefully. No, you guys don't have to. You guys have to know around roughly. So we know about 400 to 800 nanometers. And you can see we start off with the violet, pinkish, and then we go through all the way to the red. So we start off with about 400. We end up with about 780, 800, around that. So when we're thinking of this reflection, specular reflection. So the reflection, smooth surface in a single direction, and it's at a specific angle. So this angle here, see this, sorry, not that. Let's be real. Okay. So here we have a ray of light. It's coming at this direction, right? So what it's saying is this angle here is going to be the exact same angle that it's going to reflect at. That is what we call a specular reflection. So we talked about this for a good amount of time. I'm just reviewing it for now. So when it's landing on a smooth surface, so this surface is smooth. Smooth means it's nice and straight. No turns, no covers, nothing. Okay? So it's not going to move. Now, if we have a rough surface, this is when it becomes diffuse reflection. Because depending on where and how, you can see they're all scattered. This is called diffuse reflection. So going back, specular, that means uniform. That means it's going, the way it comes in, it's going out. When you have a smooth surface, now if we have a rough surface, and you can see this is like the ground, it's going to be scattered. It's going to be all over the place. There's no uniformity with it. Now, color, the wavelengths of light that it reflects. So the reflected wavelength depends on the arrangement of electrons. Again, this is all coming back to how the electrons are arranged and the materials it's made out of. It's not very important. Some light waves, they're absorbed. Light wave that gets reflected back is the one that determines the color. That's what we'll see. So because of this, it gets reflected back into our eyes, and then it gives us an idea on what the color of the object is. And this is not something new. We've kind of talked about this before. I'm just going through it a little bit. So we see the light hitting the apple. Okay? And then what we see is the red being shot back up. Now, because the red wavelength is shot back up, we perceive it as red because our eyes are able to uh, our eyes are able to decipher the wavelength of the object and its color. So the color of an opaque object is determined by which wavelength of light are more strongly reflected. So in this case, the apple is really red. It's going to absorb most of the colors, and the red light is being reflected back. Is the red light reflected? Yes, exactly. So in this case, that red apple is going to reflect that red light back, and that's how we perceive that color. Sometimes all we got to do is read a little bit. I promise you. It's not a stupid question or anything. It's just sometimes we get jittery and we start asking questions when the answer is right in front of us. Now, for example, if you guys take a look here, I have a logo on my chest. So this is a logo of Reebok. So what color can you guys see? What color can you guys see? True. So what does that mean? Thank you. So what does that mean? Yes, exactly. So that it reflects yellow and absorbs the others. Exactly. Very good. That's exactly what it means. Now you guys are pros. So wavelengths that are not reflected back. So if we get a black, this shirt is black. So that means it's not absorbed. So anything that isn't reflected back, that means it's absorbed. So if all wavelengths are reflected equally, so all wavelengths are reflected equally, that makes it appear white. So this white table, that's why sometimes waking up in the early morning and you get this shot of light, and then you have a white wall and white desk and it's just so bright. Why? Because it's reflecting all that light back up. You see what I'm saying? Now, if all wavelengths are absorbed, this sweater, the object appears black. When I was in class, we had like these colors filters, and I held up the red color filter, right, and the red color teach put on the screen I saw as white through the filter. Why is that? With no disrespect, I don't know what the heck you meant by that sentence. So you were in school, you held up a color filter, and the red color, they put a red color on the screen, and you saw white through it. You got to be serious. I have no idea what you're saying here. Yeah, I saw the red colors as white. So you had, okay, so you had a red color filter, and the teacher put a red color filter up on the screen, and you saw white. You saw a red color, but it wasn't a red color. Is that what you're saying? Okay, you had a red filter in your hand, and the teacher had a red picture on the board. Oh, okay. I looked through the red filter and you saw white. Okay, so what that means is that filter. Wait, but you saw white. I saw as white through the filter because it absorbed all the red light. That's the only thing. That's the only thing that makes sense to me. Okay, anyways, we're gonna move on. I'll see if I can understand the question a little bit later. So now let's talk about the white surface. No pigments, it reflects all of it. So for example, white in daylight, red in red light, green in green light. That's just how it is. So let's see here. Again, very, very simple. If you're seeing a white surface, it's reflecting all the lights. If you see a red surface, it is reflecting red. That's it. If you see a black surface, it is absorbing all of the light. Okay? So again, we're not going to talk about this because we already did. So we talked a lot about radiation. Let me see how many more slides. Because we already talked about this. We don't really need to talk about it again. Yeah. That's that. Okay, now we're going to go on a break. And then when we come back, we're going to do some practice questions, okay? So break time until, let's say, 7:22. Okay, go and enjoy your break until 7:22. Okay, just review. We'll do this. We'll start off with question number 16. So I want you guys to type in what you guys think for A. What is A? Okay. What is B? Nice, nice. Someone wrote all of them. Very good. Yeah, so A is microwaves, B infrared, C. You had that one locked and loaded. Good. And D. So C is visible light. Then we got ultraviolet X-rays, and then D, gamma rays. Very good. So we already established that C is for visible light. Now I want you to think here. We're gonna keep going with B. So which one of the statements about electromagnetic waves is correct? So we want to pick one. So radio waves have a higher frequency than X-rays. Is that true? Radio waves have a longer wavelength than ultraviolet. X-rays have a longer wavelength than radio waves. Or X-rays travel faster through air than ultraviolet. We know this is not true because they all travel the same. Yes, we got a few answers. What do you guys think? Yeah, so some really good answers here. So do radio waves have a longer frequency? Sorry, have a higher frequency than X-rays? No, this is not true. X-rays have higher frequency. Radio waves are far, far on the left. X-rays have longer wavelength than radio waves. Is this true? No, they have shorter wavelengths. So that leaves the second one. Very good, excellent. Okay, so let's focus on C. Give one possible danger of exposing your skin to ultraviolet radiation. Yeah, very good. So we got skin cancer. Yeah, very good. So skin cancer. What about aging? We got sunburns. Yeah, that works. Is skin cancer the most common cancer in the UK? Do we see a lot of sun here? No. By the way, I'm not laughing at you. It's just interesting that fair, but even with the excessive tanning beds, it's not really. What's interesting is I haven't met before moving to the UK. I haven't met so many people who have like fake tans. In comparison, because I'm from Canada and we get a decent amount of sun. Not like Australia, for example, but we get a decent amount of sun, and we got a lot of snow. So kind of yeah. So the most common types of cancers here in the UK is breast, prostate, lung, bowel cancer. Bowel cancer is kind of coming up. The summer weather here is really nice. But even then, I'm just saying, in terms of who gets fake tans, have you been out? Yeah, but you guys don't have the infrastructure to handle the heat that comes with the summers, man. The problem is all the homes here, they keep so much heat inside. So it gets to literally like 30 degrees inside. A lot of people do fake tans. It's actually very interesting. Not even just fake tans, just tanning beds. Yeah, so we're talking skin cancer, we're talking sunburns, we're talking aging. So we can say premature aging of the skin. Those are all valid answers. Those are all valid answers. So skin cancer, premature aging, sunburns, all valid. Okay, let's move on. So this one has two parts. So we got 2 marks. Having an X-ray taken exposes a person to ionizing radiation. So the table below gives the average radiation dose for an X-ray of the chest and an X-ray of the upper digestive system. So we can see here the upper digestive system gets about 5 millisieverts, and then the chest is 0.1. It's kind of low. The risk of an X-ray causing cancer is 1 in 20,000 for each millisievert of radiation. So compare the risk of developing cancer from having X-ray of the upper digestive system with the risk of from having an X-ray of the chest. So what are we thinking? Ooh, we got some good answers here. So with this type of question, you never want to just use your own knowledge. They have the answers right there. So I would recommend taking a look at what they have and using that. Never use your own information because you're not being assessed on your own information. And they have no way of making sure that what you're saying is correct. Okay? So very important. So what you can say, there's two ways of going about this. So we know what? That was a good answer. I don't know why you retracted it. Very good. Yeah, okay, very good. So you made a statement and you added numbers, which is really good. So what we know is based on this information. So we can look at this information here and information here. So for every 1 millisievert of radiation, for every 1 millisievert, the risk is 1 in 20,000, right? So we can write X. So we can say the risk is higher for an X-ray of the upper digestive system compared to the chest. So that could be the first thing that we write. And then a lot of you have also noted something really good. And what is that you noted? So this is the first point. So you've assessed that. Okay? So this is a good point. Okay, now we have 2 points we can kind of provide. All right. So we can tell them exactly how much. So what is that? A lot of you have already written it. So more risk by a factor of 50. That is perfect. That is completely fine. So this will also get you marks. But no one has mentioned the other way we can show it. Right? So the other way we can show it is we got a value here. 1 in 20,000. So what we can do is we can write it. So what is the chances? So for upper digestive system, we just divide. So there's 5. So 5 in 20,000. That would mean for upper digestive system, that gives us a 1 in 4,000. Okay? For chest, that gives us a what? 1 in 200,000. Because it's only 0.1 for chest. Is that true? I don't think so. But for the sake of this example. So just based off of this, we can say, dang, that's crazy. You want to try to avoid upper digestive system x-rays. It's not really needed. So for example, again, I'm just showing you the ways in which you can think about the question. And we're using information that they provided. We didn't add any, we didn't do anything different. Okay? So all we did was took the information and kind of relayed it in a way that is possible. Does anyone have any questions? I just want to find another. I think it was. Um, I forget. Here, we'll do this one because it has some of the refract indexes. Okay. So these are the parts of the eye. So a section through a human eye. We want to write a correct label A, B, C, or D in the empty boxes. So cornea, which one is this? What number? Man, you guys are talking too much. Just try to answer the question and talk later. Yes, it's B. Very good. Cornea is B. B. Okay, what is the lens? Which one is the lens? A, very good. A is the lens. Why? Because you can kind of see the muscles here and they'll stretch it out so that when light comes in, it can focus it at the back of the eye. That's what we want, right? Okay, and the retina. Where is the retina? Very good. D. Excellent. Very good. Okay, so we got a table here. And I think we're going to get cut off. So let me copy this and then paste it on the next and then I'll paste it here. Okay, so we want to look at this table here, and we're trying to describe the pattern shown in the table. So what is the pattern? So the table right here. So the table shows how a mass of 1 centimeter cubed of different materials varies with refractive index. So yeah, excellent. You can say, yeah, the proportionality wise, yeah. Um, so what you can say is if refractive index increases, mass increases. They're proportional, yeah. The pattern in the table shows that the refractive index increases, the mass also increases. Yeah, very good. It's not directly proportional, but it is proportional. So like if we have an increase in one, we're going to see an increase in the other. So that's what we can write. But we're just going to write it in regular. So mass increase as refractive index increases. Alrighty, so we can write that. Okay, so now we use lenses, and they're used for correcting visual defects often, and they have a low refractive index. We want to think of one advantage and one disadvantage of using lenses with a high refractive index for correcting visual defects. So we can use this information here. So what's an advantage of a high refractive index? Yes, very good. So is heavier an advantage or a disadvantage? No, that would be a disadvantage. Exactly, very good. So a disadvantage is it weighs more, so it's heavier. So that'd be a disadvantage. Yeah. What about advantage? Dang, why are you hoping someone fails? Exactly. So they could be made thinner. So high refractive index, they can be made thinner. Okay. So I think this will be the last question. So the eyesight of a person can change throughout their lifetime. Scientists have designed cheap spectacles that allow the wearer to change the focal length of lenses as their eyesight changes. So there's two designs. So one of them is using water-filled lenses where water is pumped in or out of the lens to change its shape, and the other uses a pair of specially shaped lenses for each eye that are able to slide across each other. And these are the two designs. So I want you to just think of some advantages and some disadvantages of each of the design. So one advantage, one disadvantage for each. Just think about it and then write it down. And I think that's where we'll end for today. Yeah. Yeah, that's absolutely fair thing to say. So water-filled lenses do not look aesthetically pleasing. So in other words, they're ugly. Fair. But it might be cheaper. Yeah, very true. Pumping water in or out allows for adjustment of the lens shape. Yeah, exactly. Very good. Design a water-filled lens are inconvenient and look chunky, easy to change. The lens, yeah. The sliding spectacles are easy to adjust, but also is more expensive than the water. Yeah, that's true. They might be a lot. They might be a more expensive. One disadvantage is first glasses are bulky looking. The other one looks light. Yeah, that's true. They might be fragile or could leak. Yeah, absolutely. Those are all very good answers. Excellent. Yeah, very good. Okay, I think you guys are done for that. We'll do this. So just pick a game. Yeah, yeah. While I read the rest of your comments. Which game would you guys like? Cold Quest? We'll go nice and simple. Because I created a blueprint. What Kahoot is less stressful? Adds tension. That's what I want. I want tension. That's a good thing. You guys are young. You guys are probably not engaging in too much activity. So you guys need the extra little. There we go. I like this. So we'll get started in a minute. Okay, we're gonna wait one more moment. If you're waiting and you have some questions, please feel free to post it in the chat. And as we're waiting, I just want to say I hope today's session helped make the topic feel a little bit clearer and you enjoyed it. So if you are finding the classes useful and you'd like to continue learning with us, you're more than welcome to join, especially those that are on trial. I'll be posting the link in the chat so you can go ahead and follow that. And yeah, it was a pleasure to have all of you in the class. So I'm gonna post that in just so I don't forget. Alrighty, we're gonna get started. There we go. No, is it frozen? Dang. Why did it do that? We're gonna have to do 7 minutes. Okay, I'm reposting the chat. It's not a sign. I'm not gonna do a Kahoot. Okay, for now. I just try to rejoin really quickly. Okay, we're gonna get started. We got one. There we are. From 200 million to 4. That's the name of the game. Nice, good. Excellent. Okay. So we're pretty much done for today. I just leave the last few moments here just to give you an opportunity to ask any questions. Wow, you guys did amazing. Some of you didn't do that great, but it's okay. It was very close. Very good. I'm impressed. No, I'm in training to become a doctor, so I don't think I'd be a teacher. Um, everyone, in my opinion, everyone's kind of born with something that they're good at naturally, and I think me being a doctor is what my calling is. And I think every person has their specific calling. So I'm good at teaching. It's something I enjoy, and I can see myself being a medical educator. But in terms of like teaching as like a school teacher, probably not. You guys frustrate me way too much. I couldn't see myself doing that every single day. Yeah. So there's medical teaching, medical education. So teaching older individuals. You guys are too hectic. With all due respect, of course. Well, yeah, you're never gonna want to do something for free. If you're good at something, you never do it for free. Unless like it's like for charity or something like that and you want to do it on your own time. Yeah, you beat me to it. Yeah. No, I think like for example, I want to work with like Doctors Without Borders, humanitarian work as a doctor and things like that. Yeah, absolutely. But what I mean is like you need to make a living too. So you can't help without being in a financial situation that can give you that. So what do I gotta say for the young adults choosing what to do in life? Honestly, you guys are in such a sticky situation, not gonna lie. You guys need to unfortunately, you guys need to figure out something that is viable and that will be a career. Um, if I knew what I know now, I would have gone into potentially computer sciences as my undergrad and then went into sciences because it would have been so much better money and so much better lifestyle going in. So you learn so much skills that are in high demand. Anything computer science, anything coding, anything, all of these, you're making so much money and you have the decent work-life balance. I know such low paid jobs, but the reality is a lot of the jobs they don't require that much skill. So you got to think about the jobs that require a decent amount of skill so that you're not easily replaced. Once you become easily replaced, whether it's by a robot, whether it's by a computer, whether it's by AI, whether it's by another human, then you become redundant. And the problem is some people they don't push themselves hard enough. And I'm not talking to the breaking point. I'm just talking to the point where you're a little bit uncomfortable. You like that easy. You like that sitting down and chilling and this and that and relaxing. Not a lot of people want to put in that hard work anymore. And you know who's going to win? Who's going to make it? Who's going to be profiting? It's those people who put in the work. We all know what's happening in the future. Why are they still making us work like this? Because if you don't, then you're just going to sit at home collecting checks from the government until they stop giving you money. Do whatever you want to do as long as it makes you happy, and as long as you don't screw other people over. That's all that matters. But anyways, it was good having you all in class, and we'll see you next week for a new topic. Take care, everyone. Bye bye.